Welcome to Filtering versus Graphics Round 2. My name is Timothy Lattis, and this is the NeoKino Graphics channel. Good place to start for the background of this one is to check out Matt's work. Dan the Man has a bootleg video of rendering the alternate history of the Order 1886. Definitely watch that one. And Matt, MJP, talks about custom MSAA resolves on his blog. That's also a good read. Going to rewind history here back to the era of TXAA, which I did at NVIDIA, after FXAA. This was an MSAA with or without SGSSAA plus a very primitive TAA. The prototype demos that somebody might have seen, the ones I built, had CSAA and scaling support in there too. However, I don't believe those made it to the final release build. Now, if Jensen didn't black box this, maybe things would have been different today. It never got a full correct integration. The reason for that is because I believe all the integrations were paid. The problem was that it was for NVIDIA only. If the thing wasn't a black box and it was just a custom resolve and it worked across all vendors, then it would have started to provide interesting solutions, especially with scaling. It would have scaling support long before DLSS, and that primitive TAA would have worked a lot better because you have multi-sample for the neighborhood. Then we have the Order 1886. This one was 4x coverage with 2x MSAA mode, and it had TAA without jitter. That without jitter part is super important because jitter is the thing that causes a lot of the artifacts in the TAAs. I believe they used a trick to maintain coverage. They would render first, nearest first with a Z prepass, and then when they shade, they would render far first. And the reason why you need to do that is there are a lot of cases where you lose coverage if you render with nearest first. I think if this game had a sequel, maybe things would be different today. NVIDIA culled CSAA from the hardware due to the fact that coverage is the order dependent. Of course, the thing that would have potentially come after CSAA as a replacement would have been different rates for depth compared to color, meaning say instead of having coverage without depth, you had coverage with depth. So I've done lots of R&D into the wrong way of doing things. In this series, I'm going to try to continue with the right way options, but I'm going to focus on a few wrong ways that I think others are going to find very useful. The first is the less wrong unorm box filter. So sometimes you want to be able to do a perceptual space box filter because you like the look, the uncanny ultra sharp look. However, you want the colors to blend in a linear way. And the way you can implement this is you do the perceptual space box filter. So that's the average of the samples inside the pixel. And then you do the linear space box filter. And then you make the linear intensity match the perceptual one. And that will maintain the gradient and give you the nice color. Another wrong way was MSSS. So this was a multi-sample scaling resolve, and this was something I did in Shader Toy. I don't think I ever released this one or made it public. The picture on the right is showing 2x area, I believe. The concept here is you'd render with 8x MSAA, and you'd support a greater than greater than or equal to min sample shading, and then scale up by 2x, 3x, or 4x area, and do that in a custom resolve. And so this one blended 3 kernels for sharper outputs. I'm doing it the wrong way. I am amplifying details at Nyquist. And so the 3 kernels were a horizontal, a vertical, and basically the intersection of the horizontal and the vertical kernels. And then I would pick the kernel that makes the output the sharpest. So I'd look at the local gradient. This one is perhaps the most useful one of doing it the wrong way. This one was showing how to do a 16x SGSSAA resolve. The hardware doesn't really do 16x MSAA, so this is all synthetic, meaning something you might do in a compute shader, not with raster. And it was using a Lenkos 2 approximation, but doing it in linear space with an adaptive filter. So this is going to amplify details at the Nyquist frequency, and it's going to rely on some amount of ringing. This kind of functions like CAS does in that it does a local analysis, and then it modulates the amount of ringing in the kernel based on how far you can push both the positive and negative lobe on the output. So what I mean by positive and negative lobe is on the darker side, you're going to go more dark, and on the lighter side, you're going to go more light. And whichever one would be signal limited, whether that's the peak signal at 1 or the minimum signal at 0, I would make sure that we don't violate that. Like we're not going to get clipped output. And this kernel this one went really far. I optimized for dot instructions. The irony, of course, is vendors don't care about dot instructions anymore. And then it was optimized for huge kernel FP16. There's some, when you start doing lots and lots of accumulation, you have to do it in a smart way. So let's talk about the next big question. This is going to continue from the first filtering versus graphics, so please watch that first if you haven't done so. The question here is, what is the best option for triangle-based CG rendering on GPUs today? I thought it'd be fun to start and do the inverse of what I did last time, and this time making modern games look like CG. So I went to the 2025 NeoGAF screenshot thread and I pulled one of the shots in there, one that was super high frequency, and maybe it had some post sharpening, basically hyper detailed, with a crazy amount of visual noise. And if we want to make this look like a CG film, I put it through a linear Gaussian with a 3 pixel radius, and I did a simple 50% nearest downsampling. And the output now looks a lot more like a CG movie. It's very clean and realistic, and this hints at a solution. However, I would never do this. I'm certainly not going to use DLAA, not going to render at screen res, then scale up to a larger resolution with screen res with, say, an MLTAA, and then downsample again. This kind of process would build in a huge cost, and it would subject everything to temporal filtering artifacts. And I have zero tolerance for temporal filtering artifacts. My base case is 0 temporal artifacts. So instead, I'm going to return to the golden age of AA, and that is the 8X SGSSAA. And for those that are not familiar with that term, this is sparse grid, supersample, anti-aliasing. So I went back to 2011 on the NeoGAF screenshot threads, and these are pretty much killed by recompression or broken links. Too bad, because there were a lot of really good old 8X SGSSAA shots in there. So if we look at the best option for triangle CG on GPUs today, this would be the best conventional option. We'll talk about another option later. It would be to render at 8X SGSSAA. So we're shading all 8 samples of 8X MSAA, and then pair that with a wide kernel custom resolve. The other thing we can do here is we can use the 2x2 programmable sample locations, and we can get 16 unique sample locations per axis per 2x2 pixels. And that'll complement the wide kernel resolve that we're going to do, which will be roughly a 6 pixel wide kernel resolve. So this will effectively make 8X MSAA look like 16X MSAA. In order to make this work, we only have one option, and that is we got to push all the shading out of screen space and into some kind of object space atlas. Therefore, when we're actually rasterizing, and we'll do rasterization once, and we're only going to grab texture data in that pixel shader. And thus we'll have fully decoupled shading from resolution and refresh rate. So there are some pluses from the hardware side, especially on NVIDIA. NVIDIA GPUs have fantastic 8X MSAA. Samples are packed into a spatial region, basically a single flat layer, and they can apply compression. NVIDIA is very fast for custom resolves, and this has been the case for over a decade now. One thing that would be great here is if PC vendors for GPUs had lossy compression too. So like the last one, this one has an associated shader toy. I'd suggest following along. I'm not going to show the thing live because of the video compression artifacts. You'll have to watch the other video to get an idea of some of the background here, so I'm not going to duplicate that stuff. This first row is 128X MSAA, which doesn't exist, using a 2x wide Lanczos 2. In other words, it is going to prune frequencies around Nyquist. This was the last one in the prior talk. It doesn't flicker, but it's too expensive to use. Now if we go to what we could do today, that would be 8X SGSSAA with the same kernel, and this would be effectively the practical GPU limit, and it does flicker a lot, especially around Nyquist. And the reason, of course, it flickers is because if you have only 8 samples per pixel, and you don't have an even distribution of the fence posts and the black, then you're going to get something that's plus 1/8 or minus 1/8. So Lanczos 2 has a lot of issues. The negative lobe means that you're using a really wide kernel, and it needs an adaptive kernel, which is quite expensive. So this next slide shows 8X SGSSAA combined with the 2x2 programmable sample locations with that same 2x wide Lanczos 2. And this gives you effectively 16x AA since you have a really wide kernel. So now the worst case flicker is a stop less, and I think this should probably be fine in real content. not this synthetic stuff, but stuff you'd actually render. So we do want to address the cost. We don't want to run Alenkos 2 because of how big it is. So one of the first options we could do would be a cubic B-spline. This would drop the kernel size, say, from 8 pixel wide to 6 pixel wide. And it does do a slightly better job of filtering out at Nyquist here because of the scale of the kernel. But we do get the same near Nyquist flicker. We could also move to potentially better kernel, like, for instance, Blackman-Harris. This one has some benefits in theory. It would have less side lobes in the frequency domain. However, it's really hard to see any difference visually, especially with the temporal flicker. So this hints at what we do next, which is if we can change the kernel and we're not seeing too much of a variation or something that's perceptually important, we can start to optimize for the cost of computing the coefficients of the kernel. And so this one is a fast kernel. I will show it later. And it's technically not as good as the prior example, but perceptually it's good enough. It's certainly good enough when you're not feeding back the results back into the kernel. So there's no temporal feedback because we're not going to do any TAA here. One other option we could do is we could do viewport jitter and just a micro jitter, so like 1/32 of a pixel. And in theory, that would slightly help break up the flicker pattern, meaning instead of seeing a very regular pattern, you'd see one that's a little bit more random. However, you cannot change the flicker amplitude with this. So that fast approximation, what is it? It's very simple. So in this case, the orange is the Blackman-Harris. It's very expensive. You'll notice it has transcendentals. And the fast approximation is my go-to for anything of a bell-shaped curve that start working with parabolics. So this is 1 minus x squared raised to the power of 4. And of course, you wouldn't raise it to the power of 4 using the pow. You would use 2 multiplies instead. So I said before that there's an even better way to do it than MSAA. And that is true. And that is, instead of rendering on MSAA, we could just rotate the rendering so we get off the regular grid. So there's some negatives with rendering with MSAA and especially SGSSAA. And that is your standard 2x2 quad occupancy issues. They get amplified. SGSSAA packs 2x2 quads for each sample index. So you get pretty expensive shading. Also, AMD's hardware with fmask is actually not good for custom resolves at all. You have indirections during resolves, and those can get pretty expensive. Also, 8x MSAA might not have the best depth compression on some hardware, and so on. So there's a lot of potential negatives. The alternative, you just do regular non-MSAA rendering of a really large target, large enough that you can rotate the viewport. And what I mean by rotating the viewport is you have to pre-fill the area that you don't want to see with z equals near to avoid rendering into that area. And the idea here is to render the viewport such that when you look at a group of pixels in a square, you get at least 16 unique x and y axis intercepts in the kernel. So I've never actually pushed it up to 16 when I did this. I focused on the 2x case or the 4x case. So yeah, a long time ago I built this. This idea was really, really good. It worked extremely well. The other motivation for doing this idea was that even though I'm rendering to a really large target, I could do my post-processing without MSAA, without a MSAA resolve. And the other thing is if you know you're going to downsample, you can change your post-processing. For instance, you can make the post-processing dither, as long as the dither is high frequency, it'll get cleaned out by the resolve kernel. So in this example, it's very synthetic. I rendered a bunch of boxes, and the boxes went from pretty large size to very, very small size. So that's it for today. I'll be cutting up details in separate videos. I'm not actually planning on building another triangle render. However, much of the know-how I think transfers to what I have in mind.